Classical Physics, Tutoring Chapter 1, Section 6, Elastic Body. The elastic body is not like rigid body. Remember, the rigid body, any 2 points inside the body, the distance is fixed. So that's the definition of rigid body. And we, in the previous video, we came up with F equals ma. Rotational movement will be torque equals moment of inertia and angular acceleration. So these two equations describe everything about the motion of rigid body. It has the 6 degrees of freedom. XYZ location, the direction for the parallel motion, and rotational movement around each axis. Okay, so that's basically Newton's mechanics. We complete anything with a point mass to the object which has a size. As long as it's a rigid body, please check the previous video. Now we get into the elastic body. Elastic body is this D change. It's not fixed. So what kind of materials like that? Okay, actually any ions or any metal, if you stretch, it's go back. The rubber band, you stretch, it's go back. So has a stretching and also bending. When you bend, then it's snap back. Okay, and the ideal elastic material means when it's bend or stretch or shrink or twist, it's go back to the original shape. That's the ideal elastic body. Well, if it doesn't go back to the original, like a plastic, you bend, then it's just bent. Okay, this is called plastic. And plasticity means how much you can deform. So deformation. Ideal elastic material, when it's deformed, like stretching, shrinking, twisting, bending, it's come back to the original shape. The stuff doesn't come back to the original state. It's called plastic. This plasticity is things deformed and it stay there. It may come back a little bit, but mostly it doesn't come back. And this is another subject. It's totally different physics, because we're dealing with the force between atoms or molecules. And plastic usually has a long organic molecules, and they are interacting each other. When you pull, the location of a long molecule change, and it won't come back. On the other hand, the metal is all the atoms lining up, and if you bend, it slightly change, but it's try to come back to the original crystal, the distance between the atoms. So it's tend to be elastic material. But this, we're talking about the molecule levels. It's beyond the classical physics. Okay, just like a friction. The friction, we cannot explain everything by Newton's law. We have to get into molecule level. So we assigned friction coefficient and deal with it. Same thing, it's an elastic material. Its molecule levels So what's happened is when you stretch the spring, the distance that stretch, it's going to be the force needed to stretch. So in this case, distance is going to be negative when you stretch. Okay, so we take this polarity, you stretch all the way, and pretty soon you don't need a force much. The other way, if you shrink spring, at some point you need a force. You don't need a force so much, it's a maximum force. But from here beyond that, you cannot shrink anymore, because the spring get shortest distance. Okay, so there is a range we can use. This linear portion, this slope of the linear portion is called Hooke's coefficient. So we can establish F equals negative HD. This negative is depend on how you take. If you take a D positive this way, then the force is going to be this way. So vector wise it's negative. So Newton's equation established, thinking this is M and point mass, the D is going to be L sine omega t. So the V d dt is V is going to be omega L cos omega t. And acceleration d double prime is negative omega 2 L sine omega t. Now using this, we put it in original Newton's equation, then we get the relationship equals h. So if we know the Hooke's constant, we can calculate omega, right? Omega is square root of h over m, and omega is 2 pi f. So frequency is going to be h over 4 pi square m. So we know how it's oscillate. When you stretch it and release, the spring go back and forth. That's the frequency is going to be this equation. Now how about energy? You stretch, so what you do is you take F, right, and d let's use x, dx, 0 to maximum distance L. That's the total work. Okay, but this work is converted to the kinetic energy at the center position here. So we can use this kinetic energy. It's much easier because we know already V. So V is omega L, because cos omega t is 0. That's the position, omega L. So energy stored by this spring is this much. So you know elastic material, when it's deformed, it has an energy, and try to come back to the lower energy state, which is original still position. Okay, so every time you stretch, bend, or shrink, you try to come back to the lower energy state. Okay, the elastic material is also called Young's module. So the Young's module, the Young's define more generalized Hooke's constant. Suppose you have some force acting on internal location F, okay, and F over S is force per area. It's called stress. And in this area, the material, elastic material deform. See how much, say it's stretch, then delta L, this location X. So this much per dx is stretch. It's called skew. And Young's assume their linear relationship. So Young's constant is delta L over L, skew, and stress, the ratio, the simply, okay? So at the location X, we can say delta X dx it's going to have L here, okay? It's going to be Fx over Es. So moving L here, and that's the equation for skew. If we apply this for this case, say we have a total weight W, and at this point F is L minus X over LW, right? So it's going to be d delta L dx is going to be that's the F. So you look at this equation, L minus X W L over Es. Okay, now this is going to be 1 minus X over L WL Es. Delta L is going to be WL Es X minus 2L and 0 to L. So if you plug in L, it's going to be the W L square Es 2Es. Okay, we have some error here. This L is extra. We don't need this L, right? Because it's a ratio per lengths. That's the ratio. We're talking about the ratio. The per lengths dx, the skew is this much. So we don't need a L. Okay, so we have extra L here, and it's going to be like that. So it's going to be W2 and LES. So if you compare with the original equation, we're talking about the average weight. So using the average weight, we can calculate this length, okay? And how much energy is stored by this elastic body, well, you calculate F and dx, the x0 to L. You take the integral again. So that's the energy. So Young's constant works for any internal stress and the skew, but that's a 3D space is going to have a Young's constant for x direction, y direction, and the z direction, right? Okay, so it's like this. When you apply force to a stick bent. So there is the Young's constant on this direction, and using this we can calculate this curve. Okay, the same thing we can do now. For the musical instrument, you have a string you pick, then it's vibrate. The vibration frequency is the multiple of this frequency. This length is L, that define the lowest frequency for this case, and we talk about this more detail in oscillation section. But they are all same. The Young's constant, once we measure the Young's constant, then with this constant we can calculate, see how much it's bend for the force, given force F, then energy stored, and vibration frequency. Okay, so elastic material, a lot of them application is to find out the vibration. And vibration based on the force, which is a stress, versus skew, and that's what is connecting them is Young's constant. So material Young's constant we measure, we can pretty much figure out how it's bent, shrink, stretch, or twist, and how it's vibrate. Okay, so that's the elastic material physics. And when the elastic material, if it doesn't come back, it's called plasticity. It's just deformed and stay there. And if you push this to the extreme, then it's become fluid. Then we need another physics. The fluid shape is determined by the container and the still case, and dynamics means the water is flowing, and how do we analyze that? That's the next section. Okay, I hope you enjoyed this video, and please check the next video, fluid dynamics. If you like, subscribe.